from your book, this is, let's see, 11.4, right? Yeah, 11.4. Polar coordinates. Hey, I want to take a quick show of hands of people that have heard of polar coordinates before. I thought that might happen. Not a whole lot of hands. Show of hands of people that plan on being at Lakeland next fall. I thought that might happen. Okay. I'll be talking to some of you today, actually. Polar coordinates. Okay. So the idea is this. Normally, when you plot points in the plane, we use, well, coordinates with a comma between them. And we know that this is x and this is y. Okay? Now these are called either rectangular coordinates, or they're sometimes called Cartesian. Anyone know why? The Cartesian plane. Do you guys know why it's called that?
Because the dude's name was like René
Descartes. Okay, so René Descartes invented, in a way, analytic geometry. The idea of doing geometry with numbers, with algebra attached to it. So they named the plane after him, okay, Cartesian. But it turns out that for many applications, we can do things more easily if we change the way we label the points in the plane. And so someone came up with, well, over the years, people have used an alternate coordinate system. And I'm going to label it R and theta. Okay? And these are what we're going to call polar coordinates. The first number will be R, and the second number will be theta. Okay? So I think as my first example for you, we're going to do the following. Let's plot the point. Let me give you 4 5/6 pi. And you know, it's funny because you've never done this before, and I haven't taught you anything yet, except for a trig class, or most of a trig class. But you know what theta usually means. What's theta? It's an angle, right? So my angle here is 5/6 pi. That probably means something to you because we've been working with radians so much. And R, we've used R a lot in this class also. R sometimes stands for a radius, but we kind of know what it means also. And I guess, since you're in a group, I thought maybe I could turn you loose and see what you do with that. Okay? And if you finish that one, if you're able to plot that, then I'm going to have you plot one more point. So next, we're going to plot the following point. Let's plot -4 and -1/6 pi. All right, so there's 2 exercises. I'm going to pause, let you try it, and then I'll show you what to do. Time out! That's all you get. I got to show it. One thing is interesting here. Usually we do X and then Y, right? But when you do polar coordinates, I'm going to make a recommendation. I'm going to make a recommendation. First, I'm going to look at the angle. Then I'll worry about R. So that's interesting. Let me show you. You haven't done this before. You shouldn't be expected to be able to do it yet. So let me go ahead and draw the angle, right? If I draw the angle 5/6 pi, can you tell me what quadrant I'm going to end up in?
2.
Okay, very good. So I will end up in quadrant 2. Matter of fact, you guys even know where I'm going to end up because that was one of those famous angles that we memorized, right? Okay, so the angle ends right there. And normally I've been drawing a radius of 1 because that's a unit circle, but I don't want to do that this time. This time I'm trying to plot 4, 5/6 pi. So my theta, as I said, is 5/6 pi. And my r, my radius, is 4. So there's 1, 2, 3, 4 times 4 times farther than just the unit circle. Are you guys with me on that? Mm-hmm. So this point right here, whatever that is the point 4, 5/6 pi. Do you guys understand? Okay. I'm going to pause and let you plot the next one. Ready? Go. Dun, dun, dun. So I heard some good thoughts. One thought was the fact that it's a negative angle tells me, how do I start this problem? Well, I'm going to rotate this direction, right? Now, it's interesting. If you rotate negative 1/6 pi, that's about the direction you're going to be if this was really 5/6 pi. Does that make sense? Yeah. But now, the next thing that's interesting is that it says that r is negative 4. Now, if r were 4, I would move this way. But the fact that r is negative 4, you know what I'm going to do? I'm going to move backwards. 1, 2, 3. You see that? Because it's a negative r. So that's interesting. And one thing that's really different, I can see right away between polar coordinates and rectangular coordinates. See, these are the same point. That's what I'm trying to get at. These are the same point. Because if I rotate down 1/6 pi this way, or if I rotate back 5/6 pi, in some ways, you just pointed in opposite directions, right? So the negative 4 says go the opposite way, and I ended up over there. That's strange. It tells you something. It tells you that if you use polar coordinates, you could have two completely different representations of the same point. But that may have occurred to some of you already, right? Matter of fact, I'm going to pause again and ask you to find at least one or maybe another representation of the same point in your group. See if you could do that. I heard it right away from several groups. Hey, you could just add 2 pi to one of the angles, and you'll be pointed the same place. Now, I don't know, did any of the groups actually come up with what the coordinates would look like? You have it?
Well, I have not the 2 pi.
What do you have?
Wouldn't it be like 4 negative 5/6 pi?
So let's see what would happen. If I did negative 5/6 pi, that would push me around over here, right? And now if I move 4, I think I would be here. So it's not quite the same point, is it? Right? But you know what I could do? If you wanted to rotate that direction, how far would you want to go? Here's 5/6 pi. 6/6 pi would bring me there. So I guess another representation would be negative, how many 6 would I need? 7/6 pi. That's right. So negative 7 pi over 6 or something like that. Does that make sense? Matter of fact, negative 7/6 pi, if you add 2 pi to that, you're adding 12 pi over 6, you're going to get back to here. So there are many ways to represent a point in polar coordinates. Okay? And you might say, well, why are we making this so complicated? Well, it turns out that sometimes this will be an easier way to identify points in the plane. Imagine you're a ship. Well, we talk about bearings all the time, right? It's 20 degrees off to the starboard or port side, and it's this far away. Okay, so we do this kind of thing in application. Now, see that red point? one exercise I might ask is this. I might want you guys to try and find the x and y coordinates of that point. And that looks like a hard task at first. I mean, you might say, well, how would I do it? All I know is that this is 4. Right? That radius, that r. Well, here's where the trigonometry comes in. Because if you want to know the x and y coordinates, actually, I bet you could tell me the x and y coordinates if I made the radius 1. That point right there where the arrow hits the line. Do you guys know what those coordinates are? The circle. Right? If r was 1, that would be on the unit circle. What point would that be? There it is. We know that that point there, right there, in the xy coordinates, right? So if I say, give me the xy coordinates of that point, my xy would be, well, 5 pi over 6. So it's negative square root of 3 over 2, comma what? 1/2. That's the x and y coordinates of that point. So now, what about the point we plotted originally? What are the x and y coordinates of this point? Well, you can kind of see that by similar triangles here, it's just going to be 4 times as much. So the y coordinate, instead of being 1/2, it's going to be 4 times 1/2. It's going to be 2. And the x coordinate, instead of being negative square root of 3 over 2, it's going to be negative square root of 3 over 2 times 4. So I guess negative 2 square root of 3. But that's not so fun. I guess I'd like a better way to do this, okay? And so there's some formulas that can help. You see, basically, if I want to get, if I have some angle theta, and if I know r, okay, if I have some angle theta, and if I know r, and I have this point, and I'd like to know what the x coordinates and the y coordinates are, there's a slick way to do it. I'm going to draw my triangle. Again, this is theta in here. And I know that the x and y coordinates are right here. But I also know that I have trigonometry to help me, right? So the sine of theta in this picture would be what? Well, it's, help me out here, guys. Y over the hypotenuse, right? Here's the right triangle. So it'll be over r. And how about the cosine theta? Well, what's that going to be? X over r. But see, what I just had was I had 4 and 5 pi over 6, and I was trying to come up with x and y coordinates. So what I can do is I can multiply both sides by r. Multiply by r. And what I get is, so if I multiply by r, I'm going to get that x equals r times the cosine of theta. And what do you think I'm going to get for y then?
Y equals r times cosine theta?
R times
Oh, sine theta?
sine of theta. And actually, I should check and see that that works. Take the problem we just had. We had that my r theta in the last problem was 4 and 5/6 pi. So if I want to get the x and y coordinates, I can use that formula, right? I can say x equals 4 times the cosine of 5, 6 pi. And we know the cosine of 5, 6 pi. You guys already told me that was negative radical 3 over 2. And so, just like that, I get x is negative 2 radical 3. That was the x coordinate we came up with. And similarly, if I have y equals 4 times the sine of 5, 6 pi, I get 4 times, what's the sine of 5, 6 pi? We talked about that. 1/2. And so I get y equals 2. You see that? So this shows me how to go back and forth in a way. Well, no. It shows me how to go forth. It shows me how if I give you polar coordinates, you can use some formulas here with the trigonometry to come up with rectangular coordinates. But I guess the next step is going to be to go backwards. Okay. Do you guys have questions so far? Yeah, Justin.
Would it make a difference though, like when the radius is like -4? Would you make it then negative?
Here, let's imagine we did that instead. Suppose that I tried the problem. R theta is -4, and then what did we have for our? Wasn't it negative 1/6 pi was the same thing, right? That's what we had. And I guess the question is, would these formulas still work? So again, x equals, well, if we want to use r cosine theta, it's going to be -4 times the cosine of -1/6 pi, right? So I get -4, and I guess what the question is what does this equal right here? Do you guys know the cosine of -1/6 pi? Let me draw that again. Well, that's rotating down here, right? And so what would it be? That one's positive square root of 3 over 2. So I still have a negative times a positive. I'm still going to get x equals -2 square root of 3, just like I did up above. So no, it won't matter. The reason it won't matter is these cosine and sine functions are circular. They take care of it, right? Because of the way that they operate. So these formulas, x equals r cosine theta and y equals r sine theta, in a sense, they're foolproof for going forward here to come up with your rectangular coordinates. All right? So, but the next thing is, I may have a rectangular coordinate, and I say, hey, let's change it to polar coordinates. And you might say, well, how would I do that? So let's do that next. So let me go ahead and try this as a little exercise. We're going to plot the point. So let me give you that the rectangular coordinates are 1, 3. Okay, so I can plot that. Here's 1. Okay, and up here somewhere is 3. And I guess the question might be, hey, let's find some polar coordinates. Hint, use trigonometry. I think I better give you a full minute to talk about this, maybe 90 seconds. Let's see what your group can do. It's a tricky problem. So I saw some people got R by drawing this picture like that, right? Because you know 2 of these 3 sides, right? We don't know R, but we do know that this is 1 and this is 3. Am I right? So then how do you get R? Okay, so you say that R squared is equal to Right. I mean, really what you're doing is this, right? X squared plus y squared is r squared. That is another important formula for polar coordinates. So in this particular example, you guys were trying to find r, and so what'd you do? You did 1 squared plus 3 squared, right? So you got 1 plus 9 is 10. So r squared is 10, and therefore r is... Yeah, now it's interesting. I know the algebra rule. When I take the square root, I have to put a plus or minus. And we've seen that sometimes you want a negative r. Does that make sense to people? Okay? Kind of depends on the angle here. Now, what about finding that angle? Well, let me call it theta. Idea of how to find theta. Oh, we didn't come up with that yet. Maybe the picture will help. I'll pause and give you another 30 seconds to come up with a way to find theta. All right. Here I go. What'd you come up with? Do you have a trig equation for me? What trig function did you guys use?
Arc
Tangent, cosine, any others? So tangent and cosine I heard. I'm going to use tangent because, in general, the tangent of theta has to equal what here? Well, yeah, 3. How'd you get 3? Because you did 3 over 1. But isn't it true in general that it's going to be y divided by what? X. And that, I would say, is the fourth big equation we need for going from, say, in this example, rectangular to polar coordinates. Now, I heard people say, hey, I want to take the inverse trig function. And you can. That'll get you one angle. But we know how many angles are there that would actually work. How many? Infinitely many, because we know we can keep rotating. Okay? But this is going to get you one of them. Okay? And so I guess what you guys did in this example is you did the arc tangent of 3. And not that I really know what that is. Okay? That's not one I have memorized. But that's a representation of that angle. So if I wanted to, I could say that the polar coordinates, and you'll see our book does this. I mean, I could use a calculator and get you a decimal, but they'll just list it like this. They'll say square root of 10, comma. Oh no, they don't write tan inverse. They'll write arc tan of 3, and that might be an answer. Does that make sense to people?
Yeah, we use the law of cosines to find theta.
You did?
Yes.
Sweet.
We got the same answer.
How'd you do it? Oh, I see. Because but first you had to find r.
Yeah.
Then that works fine. Okay? I guess the advantage of this, it's faster. I already have x and y. I don't even need r. Okay? But yes, that's a great way to do it. And actually, the law of cosines may come in handy a little bit later for some of the stuff we want to do. So I'm already at 10:07. I better kind of stop talking here for a moment. First of all, to answer a couple of questions, a lot of people were just working on problem 42, and it was kind of like this one we just did. The coordinates were not quite as nice. We had, let's see, in problem 42, they gave me which kind of coordinates? Rectangular, right? And it was square root of 2, square root of 2? No, there's a negative by one of them. Which one?
Yes.
The x is negative? Okay. So people knew that I can find the r and the theta using those two formulas. R is going to be, well, r squared is going to be negative radical 2 squared plus radical 2 squared, right? So r squared is going to be, hey, 2 plus 2. Right? So r squared is 4. So r is plus or minus the square root of 4. So I'm either going to put a plus or minus 2 for my radius. Who's with me so far? This okay? All right, so I got r. Now for theta, I do the tangent of theta is square root of 2 over negative square root of 2. So really what you have is you have the tangent of theta is negative 1. So some people typed in inverse tangent of negative 1, and that is correct. People that had it in radian mode, you got some decimal that you weren't very familiar with. And if you had it in degree mode, you probably would be familiar with it. But one thing I want you to do actually is kind of check here for a minute. Let's suppose I drew a picture. Where would that be? Negative radical 2, radical 2. Which quadrant would it be in? Quadrant 2? Okay. Because I go to the left for the negative number, and then I go up the same amount. So really, it's kind of the diagonal of a square here, right? Negative square root of 2, square root of 2. So one thing you might ask is, can you predict what you think that angle theta should be, right? That's what theta should be. So what would that theta be? If it's going up at, well, a 45-degree angle, right? It's going, that's a 45-degree angle if it's negative radical 2, radical 2. Do you see that? So what should my theta be in radians, let's say?
3 pi over 4?
3 pi over 4. Now let me get the calculator out. And yeah, mine's not out yet, so it's going to take me just a second here. I want to just show you that if you typed in tangent of 3 pi over 4, you would indeed get that negative 1, right? So you can check these things as you go. I guess that's really the take-home message here. I better check my mode, because I'm probably, it seems like lately I've been in degree mode. Let me go back to radian. And now let me type in, for example, the tangent of 3 pi over 4. Yeah, that's negative 1. So it really works. If you typed in inverse tangent of negative 1, oh, you wouldn't get 3 pi over 4. You'd get some negative angle, right? Let me divide by pi, see if you recognize it. Just get the pi out of there. Do you recognize this decimal? Sure, what is that? What fraction is that?
1/4.
That's 1/4, right? So, in other words, if I did this problem using inverse tangent, it would look like this. Theta is the inverse tangent of, well, negative 1. What I would have gotten is theta is, what would it be? Negative pi over 4, right? Now, would that work? What quadrant would that put me in? That put me down here in quadrant 4, right? There's negative pi over 4. And if I use that, then in order to get there, what do I need for my r? Negative 2. So here's a couple of different answers. You can have negative 2, negative pi over 4, or you could have, as we did earlier, 2, 3 pi over 4. So there's a couple of different answers that would work here. Does that make some sense? Okay. Now I want to tell you kind of where we're going next with this. This is just plotting points. Remember after we plotted points in algebra class, Then what do we do next with the x and y coordinates? Equations. What kind of things do we graph? Well, we kept it simple first. We graphed lines. Remember that? And then eventually we did all the stuff you did in your college algebra class. Parabolas, hyperbolas, right? All these things. It turns out that lines actually, well, some lines are easy and some lines are not so easy in polar coordinates. But there are some things that are very simple in polar coordinates. Okay? And we'll see how this all works. So, for example, I might say I want to sketch a graph of the equation. How about I say r squared equals 9? R squared equals 9. Of course, I guess what I could be saying equivalently is that r equals what?
3.
3 plus or minus 3, right? Now, if you were to plot all the points in the plane whose radius is plus or minus 3, well, let's see. Here's one of them. Here's one of them. What if you plotted all of them? What would it look like? It would look like a circle. That's right. Right? There would be all the points whose radius is 3. So polar coordinates are like the best when it comes to plotting circles. By the way, remember one of those equations we had about r squared. What does r squared equal, according to your gray box right there? X squared plus y squared also equals 9. Do you guys recognize this equation from your college algebra class? What's that the equation of? That's the equation of a circle with radius, what?
1.
Almost. Remember, it was x squared plus y squared is r squared. So what's the radius? 3. Okay? So it's kind of interesting. You can go back and forth from polar equations to rectangular equations as well. Okay? So that's something else we're going to do. Let's see what else I want to do for you here. Oh, here we go. I'm going to show you a couple other things we can do. Here's an old college algebra problem. Find the equation of the line. Y equals x plus 2, written in polar coordinates. Now, actually, this is kind of a stupid way to handle a line. It's a great way to handle a circle, but let's do it anyways. It's a good exercise. So, first of all, a picture. We know how to graph y equals x plus 2. What do? Start off graphing what point? Okay. So this is the point. What's that thing called? That's the y-intercept. And then to get the rest of the line, what do I want to do? Use the slope and go up 1 over 1. You guys remember this? This is all from algebra, right? So there's y equals x plus 2. Well, you can imagine that the polar equation of that could be pretty complicated because your r changes a lot. And your theta is kind of where you're pointing. Let me show you how this works. I'm going to write down the equation y equals x plus 2. And now where it used to say y, remember we had an expression for y? What does y equal? R times sine theta. That's right. So I'm going to write r sine theta equals what? R cosine theta, because that's what x is, plus 2. So there it is, guys. That's an equation in polar coordinates. You might say, well, that's simple. Okay. But I want to show you something you can do with this calculator, too. I don't know if you've seen this. If you hit the mode button, you know, all year long, we have been dealing with radians and degrees. If you go down one more level, that FUNC stands for function. But what that really is a function in x and y coordinates. I want you to notice something. If I go to the right 2 spaces, you see that POL? Guess what that stands for? Press enter. And now, when you want to graph something, usually what button do I press? Let's press it again, y equals. You're right, we're going to press graph, but first we're going to have y equals. And you notice you press it, it doesn't say y equals anymore. Do you see what it says? R equals. Because basically, we want to write r as a function of theta. Now watch how this works. One of the problems here is I have r's on both sides of the equation. That's no good. Let's get all the r's on one side of the equation. So what am I going to do? I'll write r sine theta minus r cosine theta equals 2. Any guess what I'm going to do next? Yes, factor out the r because I really only want one of them. So the next step is r times sine theta minus cosine theta is equal to 2. And now the last step, r equals 2 divided by sine theta minus cosine theta. That's what I'm going to type into the calculator. When you type it in, guys, you want to put the whole denominator in parentheses so that, you know, it divides by that entire thing. So watch what we do. Let's see. R equals 2 divided by, open parentheses, sine. Now, how do you get theta? Well, if you look where you used to type in x, t, theta, or n, just press it. It's going to give you a nice little theta because it knows we're in the polar mode. So sine theta, I'll close the parentheses. We need a minus sign. Cosine theta, close parentheses twice, and I'm ready. I'm going to press graph, see what it looks like. Check that out. I got a line. You guys with me? It got real quiet. If I want to graph a circle of radius 3, here, I'll just do it in R2. R equals 3. Graph. Hey, how come that didn't look like a circle? Yeah, it has to do with the zoom. See, the way that your standard window works, it's 10 across and 10 up and down, but this shape is a rectangular screen. So each little piece of graph paper is a rectangle. If you want to fix it so it really looks like a circle, you could do that by hitting zoom square, and that'll make sure that all the graph paper are squares, and now it'll look more like a real circle. You guys see that? So that's kind of nice. Okay. Well, okay, I only have 2 more problems that I had planned for today's lecture, which is good because, like I said, I'm running short of paper here and time. I thought I would try this one next. If I give you a circle with center 0, -4, passing through the origin. And if I ask you guys, can you please graph that or write its equation in polar coordinates? Well, I don't know if you would know how to do that right away. Let's draw a picture of it. So the fact that the center is 0, -4, let me plot this point down here and call this point 0, -4. That's the center. And so if it passes through the origin, it's this kind of a picture I'm looking at. Now, I'm guessing that if I write this equation from college algebra, this is going to be something you'll remember. Let's see if you do. X minus h squared plus, do you know what I'm going to write next? Y minus k squared equals r squared. I want to write that equation down. Okay? And once I write that equation down, I can fill some things in. What are h and k? Do you remember what those letters stand for? Horizontal and vertical? Yeah. H and k is the coordinates of the center. Okay? So when I say, hey guys, we have a circle with center 0, -4, you could write it this way. X minus 0 squared plus, do you know what I'm going to write here? We would write y plus 4 squared, right? Because y minus -4 is y plus 4. And now I guess what else I need is r squared. Do we know the radius?
Yes.
What's the radius? It's 4. Because it's centered at 0, -4, and it goes through the origin. Now sometimes you might have to use the distance formula to find the radius or something. But it's definitely going to be 4 squared. So my equation in rectangular coordinates is x squared plus y plus 4 squared equals 16. But this is a hard thing to use your graphing calculator for. Matter of fact, in college algebra, we usually didn't use it. Say I want to graph it, though. In polar coordinates, I'll be able to do it. So let's change to polar coordinates. I would let you guys do it, but we're running short of time. I'm going to go through, and you just stop me if you have a problem with this. Where it says x, you know what I'm going to write? R cosine theta. So let's write r cosine theta being squared plus, and where it says y, I'm going to write r sine theta. I also have a plus 4. That's being squared. And all that equals 16. Now this gets a little bit messy. This first thing when I square it is r squared cosine squared theta. Right? Because the r is squared and the cosine squared. Hey guys, that's a binomial. When I square a binomial, I get a, you know what kind of polynomial? Trinomial. All right, let me write it out for you. That piece is going to be r squared sine squared theta plus, well, it's going to be 2 times 4 times r sine theta. That's the middle term. And then plus 16 equals 16. And this is really messy and ugly. But one thing that's really beautiful here, you can start doing some things that are really nice. Now watch this. From the first two terms, I'm going to factor out the r squared. And I'm left with cosine squared theta plus sine squared theta. Does that ring a bell to anybody, what that equals? Ah, the identity, right? That equals 1. So the beginning of this is just going to say r squared. Now the next piece here I have plus 8r sine theta. So I have r squared plus 8r sine theta. And then I have plus 16 equals 16. So if I subtract 16 from both sides, I just have equals what? 0. All right. Next, moving up here. If I divide both sides by r, it's going to say r plus 8 sine theta equals 0. So what does r equal? Negative 8 sine of theta. Wow. All that, 10:45, and I'm going to finish by typing in negative 8 sine theta and graph it and see that it really does give me the circle that I want. That's the one right there. Right? So it worked. Work hard this week on the homework, guys, and I'll see you next week.